Hey, I'm glad you're here. Whatever today brought you, the worries, the noise, the unfinished thoughts, you don't need any of that right now. Those things can wait. They'll be exactly where you left them tomorrow morning, I promise. Tonight, you don't have to figure anything out. You don't have to be productive or useful or ready for anything. You just have to be here. So if you want, let your shoulders drop a little. Let your breathing slow down. There's nowhere to be right now. Nowhere at all. And when you're ready, I'll tell you something wonderful about the ocean. Not the surface, deeper. Into a world that most humans will never see, and that science is still in the early stages of understanding. There's something oddly calming about that. The idea that there are still places on this planet that remain genuinely unknown. So let's go there together. No rush. We have all night. The ocean covers approximately 71% of Earth's surface. Not at the surface where the waves are, but deeper, much deeper, into a world that most humans will never see, and that science is still in the early stages of understanding. There's something oddly calming about that. The idea that there are still places on this planet that remain genuinely unknown, that exploration is still possible, that the Earth still has secrets. So let's go there together, slowly. The ocean covers approximately 71% of Earth's surface. It holds about 97% of all the water on the planet. And yet, according to current estimates, more than 80% of it remains unmapped and unexplored in any meaningful detail. We have more detailed maps of the surface of Mars than we do of our own ocean floor. That's not a criticism. It's a reflection of how difficult deep ocean exploration actually is. The pressure at the deepest points exceeds 1,000 times the atmospheric pressure at sea level. Sending equipment down there, keeping it functioning, and retrieving useful data is an enormous engineering challenge. The deepest point in the ocean is called the Challenger Deep, located in the Mariana Trench in the western Pacific Ocean. It sits at approximately 10,935 meters below sea level, nearly 11 kilometers straight down. If you placed Mount Everest at the bottom of the Challenger Deep, its summit would still be more than a mile underwater. Only a handful of humans have ever descended to that depth. The first crewed descent took place in 1960, when oceanographer Jacques Piccard and US Navy Lieutenant Don Walsh reached the bottom aboard a vessel called the Trieste. The descent took nearly 5 hours. They spent about 20 minutes at the bottom before ascending. When they arrived, they made an unexpected observation. In the sediment at the bottom, under crushing pressure and in complete darkness, they saw a flatfish. Life persisting in conditions that seemed to make it impossible. That was 1960. In many ways, it set the tone for everything ocean science has discovered since. The ocean keeps confounding expectations. The average depth of the ocean is about 3,688 meters. But the ocean is not one uniform environment. It's a layered system with fundamentally different conditions at different depths. Scientists divide it into distinct zones, each with its own pressure range, temperature, light levels, and communities of organisms. Let's go through them slowly, from the surface down. Think of it as a descent, a quiet one. The uppermost layer of the ocean is called the sunlight zone, or, in scientific terminology, the epipelagic zone. It extends from the surface down to about 200 meters. This is the layer most people picture when they think of the ocean. Sunlight penetrates fully here. Photosynthesis is possible. Phytoplankton, microscopic plant-like organisms, form the base of almost the entire ocean food web in this zone. Despite their size, they are responsible for producing roughly half of all the oxygen in Earth's atmosphere. Every second breath you take was made possible, in part, by organisms too small to see with the naked eye, drifting at the ocean's surface. Below 200 meters, sunlight begins to fade. The layer between 200 and 1,000 meters is called the twilight zone, the mesopelagic zone. Some faint blue light filters down here during the day, but it's not enough for photosynthesis. Temperatures drop significantly. Pressure increases. Many of the animals that live here are adapted to both extremes of this zone. They migrate vertically every day, rising toward the surface at night to feed, then descending back into the dark and cold during daylight hours to avoid predators. This daily vertical migration is one of the largest mass movements of biomass on the planet. Billions of animals moving up and down through hundreds of meters of water, twice a day, every day. Below 1,000 meters is the midnight zone, the bathypelagic zone. No sunlight reaches here at all, not even a trace. The water is near freezing. Pressure is between 100 and 400 times atmospheric pressure. Food is scarce, and yet life is here. Animals in the midnight zone have developed extraordinary adaptations. Many produce their own light through a process called bioluminescence, chemical reactions in specialized cells that generate a cold, blue-green glow. It's estimated that 76% of deep-sea animals are bioluminescent. In the midnight zone, bioluminescence is not a curiosity. It's the primary form of communication, predation, and defense. The anglerfish, which many people recognize from documentary footage, is one example. The female, which is the larger of the two sexes, dangles a bioluminescent lure from a modified spine on her head, attracting prey in the absolute darkness. The light comes from bacteria living symbiotically inside the lure. It's not the fish generating the light at all, it's the bacteria. Below 4,000 meters is the abyssal zone. Vast, flat, cold plains of sediment covering much of the deep ocean floor. And below 6,000 meters, in the narrow trenches that cut into the ocean floor, is the Hydrothermal zone, named after Hades, the Greek underworld. These zones were named in an era when scientists believed the deep ocean was largely lifeless. That assumption turned out to be wrong. Very wrong. Let your breathing slow down a little. We're going deeper. In 1977, a team of scientists aboard the research submersible Alvin descended to the seafloor near the Galapagos Islands, expecting to find, as most deep-sea surveys had found before, relatively barren sediment. What they discovered instead changed biology permanently. At a depth of about 2,500 meters, they found hydrothermal vents, cracks in the ocean floor where superheated, mineral-rich water was being pushed up from beneath the Earth's crust. The water emerging from these vents can reach temperatures above 400 degrees Celsius, though it remains liquid due to the extreme pressure. Around these vents was an ecosystem unlike anything previously described. Giant tube worms up to 2 meters long, clustered in dense colonies. White crabs, clams the size of dinner plates, mats of bacteria covering every surface. None of these organisms depended on sunlight, not directly, not indirectly. The entire food web was powered by a process called chemosynthesis, bacteria converting the chemical energy in hydrogen sulfide and other compounds venting from the seafloor into organic matter. A completely independent energy source. An ecosystem that sunlight had nothing to do with. Before 1977, the assumption in biology was essentially universal. All life on Earth depends on the sun. Hydrothermal vents demonstrated that this assumption was wrong. Life, it turned out, was more flexible than anyone had imagined. This discovery had, and continues to have, significant implications for astrobiology. If life can thrive without sunlight, supported entirely by chemical energy from a planetary interior, then the requirements for life elsewhere in the universe become considerably less restrictive. Moons like Europa, orbiting Jupiter, are believed to have liquid oceans beneath their icy surfaces, potentially heated by tidal forces from Jupiter's gravity. Hydrothermal vents may exist there too, and where there are hydrothermal vents, there may be life. The tube worms found at hydrothermal vents, Riftia pachyptila is the scientific name, have no digestive system, no mouth, no stomach, no intestines. Their body cavity is filled almost entirely with a specialized organ called a trophosome, which houses billions of chemosynthetic bacteria. The worms provide the bacteria with a stable environment and access to the chemicals they need. The bacteria provide the worms with nutrition, a complete, self-contained partnership operating in permanent darkness at the bottom of the ocean. There are currently more than 700 known hydrothermal vent sites in the world's oceans. Scientists estimate the actual number could be in the thousands. Each one is its own isolated ecosystem, separated from others by stretches of barren seafloor that act as barriers. The species assemblages at different vent sites around the world are often quite distinct. Animals that evolved independently, adapted to the same extreme conditions, arriving at similar solutions through different evolutionary paths. The deep ocean, it turns out, is not empty. It is full of life we are only beginning to understand. The ocean is not still. Even in its deepest, darkest regions, water is moving. The global ocean circulation system, sometimes called the thermohaline circulation, or more informally, the ocean conveyor belt, is one of the most important physical processes on Earth. It regulates climate. It distributes heat. It moves nutrients and oxygen to parts of the ocean that would otherwise be stagnant. And it operates on timescales that are difficult to fully comprehend. The system works because of two properties of seawater: temperature and salinity. Cold water is denser than warm water. Salty water is denser than fresh water. When surface water in the North Atlantic becomes cold enough and salty enough, through evaporation and heat loss to the atmosphere, it sinks. It sinks to the bottom of the ocean and begins moving southward along the seafloor. This sinking motion at high latitudes drives the circulation of the entire ocean. Water that sinks in the North Atlantic spreads across the deep Atlantic, eventually reaching the Southern Ocean, where it mixes and rises again. Some of it flows into the deep Indian and Pacific Oceans. Eventually, after a journey that takes roughly 1,000 years to complete a full circuit, it returns to the surface and makes its way back to the North Atlantic. A water molecule in the deep Pacific Ocean today may have last been at the surface 1,000 years ago. It has been traveling through the dark, slowly, for a millennium. This circulation has a profound effect on the climate of the North Atlantic region. The Gulf Stream, a surface current that carries warm water from the tropical Atlantic northward, is part of this larger system. It's one of the reasons that Western Europe has a relatively mild climate compared to other regions at the same latitude. London, for instance, sits at roughly the same latitude as parts of Canada, where temperatures regularly reach minus 30 degrees Celsius in winter. The ocean keeps Europe warm. There is scientific concern that climate change could disrupt this circulation system. Melting ice sheets are adding large amounts of fresh water to the North Atlantic, reducing its salinity and therefore its density. less dense water doesn't sink as readily. If the circulation weakens significantly, it could alter weather patterns across the entire North Atlantic region in ways that are difficult to predict with precision. The ocean and the atmosphere are deeply interconnected. What happens in one affects the other, on timescales ranging from days to millennia. Take a slow breath. Notice your chest rising and falling. The atmosphere you're breathing has been in contact with the ocean surface. Oxygen produced by marine phytoplankton. Carbon dioxide exchanged across the air-sea interface. The ocean is in the air you're breathing right now, in a very direct sense. It's closer than you think. Sound travels very differently in water than it does in air. In air, sound moves at roughly 343 meters per second. In seawater, it travels at approximately 1,500 meters per second, more than 4 times faster. And the ocean has a remarkable property that allows certain frequencies of sound to travel extraordinary distances without losing much energy. At a depth of roughly 600 to 1,000 meters, there is a layer called the SOFAR channel, an acronym for sound fixing and ranging. The temperature and pressure conditions in this layer create an acoustic waveguide. Sound waves that enter the channel are bent back toward it rather than dispersing outward, effectively trapping them. Low-frequency sounds transmitted into the SOFAR channel can travel thousands of kilometers before they fade significantly. The US Navy discovered and documented this channel in the 1940s and used it for military purposes. But the ocean had been using it much longer. Baleen whales, blue whales, fin whales, humpbacks produce some of the loudest biological sounds on Earth. Blue whale calls can reach intensities of 188 decibels, louder than a jet engine at close range, though at frequencies too low for human ears to hear without assistance. These calls propagate through the SOFAR channel and can potentially be detected by other whales thousands of kilometers away. The function of these calls is still partially understood and partially speculative. They appear to be involved in mate attraction, individual identification, and possibly navigation. Blue whales are largely solitary animals that may spend their lives separated by vast stretches of ocean. Their songs are, among other things, a way of maintaining contact across distances that no visual or chemical signal could bridge. In 1989, a US Navy hydrophone array originally designed to track Soviet submarines picked up an unusual signal. It was a whale call, but at a frequency of 52 Hz, considerably higher than the calls of any known baleen whale species. The signal had been detectable since at least 1989 and reappeared each year, migrating in patterns consistent with a large whale. No other whale of the same type has ever been detected. No visual identification has been confirmed. The animal that produces this call, if it is a single animal, has never been directly observed. It became known informally as the 52 Hz whale, and in popular writing sometimes as the loneliest whale, the implication being that its unusual call frequency means no other whale can hear it. Scientists caution that this interpretation goes beyond what the data actually supports. The whale may communicate perfectly well in other frequency ranges. Its biology is unknown. But the story captured something real about the ocean. How little we can directly observe of what goes on beneath the surface. The ocean is full of sounds we are only beginning to document. Sounds from animals we haven't described yet. From geological processes we don't fully understand. From biological interactions that remain entirely unstudied. The ocean is, acoustically, one of the richest environments on Earth, and most of it we have never listened to. Below about 200 meters, sunlight is gone. But the ocean is not entirely dark. Bioluminescence, the production of light through biological chemical reactions, is extraordinarily common in the marine environment. In the deep sea, as mentioned earlier, the majority of animal species are capable of producing light. But bioluminescence is not limited to the deep ocean. It occurs at every depth in an enormous range of organisms. The chemical process is consistent across most bioluminescent organisms. A molecule called luciferin is oxidized in the presence of an enzyme called luciferase, releasing energy in the form of light. The reaction is highly efficient. Almost no energy is lost as heat. By comparison, a standard incandescent light bulb converts only about 5% of its energy input into visible light. Bioluminescent organisms convert close to 100%. On some coastlines, particularly where the water is warm and nutrient-rich, bioluminescent plankton called dinoflagellates can reach such high densities that the water itself appears to glow when disturbed. Waves break in blue-white light. Footprints in the wet sand glow briefly. Fish moving through the water leave luminous trails. This phenomenon has been documented throughout human history. Sailors wrote about it in ship logs for centuries without understanding the cause. In some accounts, it was interpreted as supernatural. The scientific explanation, unicellular organisms producing light in response to mechanical disturbance, was not fully established until the 19th century. The light produced by a single dinoflagellate is invisible to the naked eye. But at concentrations of hundreds of thousands of cells per litre, the cumulative effect is visible and striking. A bloom of sufficient density can make an entire bay glow. There are specific locations around the world, bioluminescent bays in Puerto Rico and Jamaica among them, where this phenomenon occurs with enough consistency that it has become a documented ecological feature. In the deep ocean, bioluminescence serves multiple specific functions. Some predators use it to attract prey. The anglerfish lure is one example. Some animals use counter-illumination. They produce light on their ventral surface to match the faint downwelling light from above, making themselves effectively invisible when viewed from below. Some squid species use bioluminescence for communication, producing rapid, complex patterns of light across their skin. The firefly squid, Wattisenia scintillans, migrates to shallow waters off the coast of Japan each spring to spawn. Millions of them appear simultaneously, producing synchronous pulses of blue light across enormous areas of water. The event has been observed for centuries by fishermen and coastal communities and continues today. There is something remarkable about light being used as a primary language in an environment where, for billions of years, light from the sun never reached. The deep ocean didn't wait for sunlight. It made its own. Let your eyes relax. There's nothing to look at right now. Just the darkness behind your eyelids and the thought of all that quiet, cold light moving through water far below. The deep sea presents a set of conditions that would be fatal to most surface life. Crushing pressure, near freezing temperatures, complete darkness, and severe food scarcity. The animals that have adapted to these conditions over millions of years have developed some of the most unusual physiologies on Earth. Pressure is perhaps the most fundamental challenge. At the bottom of the Mariana Trench, pressure is approximately 1,086 times greater than at sea level. This pressure would collapse the air spaces in human lungs instantly. It would force nitrogen into solution in the blood at fatal concentrations. It would destroy cell membranes. Deep-sea animals cope with this in several ways. Many have no internal gas-filled spaces at all, no swim bladders, no air cavities. Their cell membranes are composed of different lipids than surface animals, lipids that remain flexible at low temperatures and high pressures rather than solidifying. Their proteins are structurally adapted to function under conditions that would cause surface proteins to denature and stop working. The snailfish, species of the family Liparidae, currently holds the record for the deepest fish ever recorded, having been documented at depths exceeding 8,300 meters in the Mariana Trench. They are small, translucent, gelatinous-looking animals, quite unlike the robust deep-sea monsters of popular imagination. Their bodies are so adapted to high pressure that they cannot survive if brought rapidly to the surface. The pressure differential would be fatal. Many deep-sea fish also have extremely reduced metabolisms. Food falls from above in the form of what marine biologists call marine snow, a continuous, slow rain of organic particles including dead phytoplankton, fecal matter, and the remains of dead animals. It's sparse. A deep-sea fish might go weeks or months between substantial meals. Their metabolic rates are correspondingly low, and their growth and reproductive rates are slow. The Greenland shark is not a deep-sea species, but it inhabits very cold, very deep waters in the North Atlantic and Arctic and demonstrates an extreme version of this pattern. Its metabolic rate is among the lowest measured in any vertebrate. It grows at a rate of roughly 1 centimeter per year. It reaches sexual maturity at approximately 150 years of age. In 2016, researchers published a study estimating the age of individual Greenland sharks using radiocarbon dating of the crystalline tissue in their eyes, tissue laid down at birth that doesn't metabolize. The oldest individual in the study was estimated to be between 272 and 512 years old, with a central estimate of around 392 years. A shark swimming slowly through cold, dark water. Today may have been born before the first European colonies were established in North America. The deep ocean operates on timescales that are difficult to hold in mind. Animals there live slowly and long. Geological features form over millions of years. Water that sank to the bottom 1,000 years ago is still moving through the abyssal plains. Let your mind slow down to match that pace for a moment. There's no rush. Everything has time. Coral reefs occupy less than 0.1% of the ocean floor, yet they support an estimated 25% of all marine species. They are, by any measure, among the most biologically productive ecosystems on Earth. A coral reef looks like rock. It is not rock. It is built entirely by living animals, coral polyps, which are small, soft-bodied creatures related to jellyfish and sea anemones. Each polyp secretes a calcium carbonate skeleton around its body. Over years, decades, and centuries, the accumulated skeletons of billions of polyps form the physical structure of the reef. The Great Barrier Reef, off the coast of northeastern Australia, is the largest coral reef system on Earth. It stretches over 2,300 kilometers and is composed of more than 2,900 individual reefs and 900 islands. It is large enough to be visible from space. Its structure has been built over roughly 20,000 years, though parts of the underlying limestone bed are much older. The biology of reef-building corals depends on a remarkable symbiotic relationship. Living inside the tissues of coral polyps are microscopic algae called zooxanthellae. These algae photosynthesize. They capture sunlight and convert it to chemical energy. They provide the coral with up to 90% of its energy needs. In return, they receive a protected environment and access to the nutrients the coral produces as metabolic waste. The coral provides shelter. The algae provide food. Neither does well without the other. This relationship is also what makes corals vulnerable. When water temperatures rise significantly, even by 1 or 2 degrees Celsius above the normal seasonal maximum, the relationship breaks down. The zooxanthellae produce reactive oxygen compounds that become toxic to the coral at elevated temperatures. The coral expels them. Without the algae, the coral loses its color, revealing the white calcium carbonate skeleton beneath. This is called coral bleaching. A bleached coral is not dead. It is stressed and it is starving. If temperatures return to normal within a few weeks, the zooxanthellae can recolonize and the coral can recover. If elevated temperatures persist, the coral dies. Mass bleaching events, once rare, have become more frequent and more severe as ocean temperatures have increased. The Great Barrier Reef has experienced several major bleaching events in recent decades. The long-term consequences for reef ecosystems globally are a major focus of current marine biology research. Coral reefs also provide coastal protection. The physical structure of the reef dissipates wave energy before it reaches the shore. They support fisheries that hundreds of millions of people depend on for protein. They are sources of bioactive compounds used in medicine. The economic value of reef ecosystems globally is estimated in the hundreds of billions of dollars per year, and they are quietly extraordinary to think about. Billions of small animals, each one adding its tiny skeleton to a structure that has been growing for thousands of years. Each individual polyp lives and dies in its small space, unaware that it is contributing to something that can be seen from orbit. Small, patient, cumulative. Things built slowly over time often turn out to be the most extraordinary. The ocean is Earth's largest active carbon reservoir. Since the beginning of the industrial era, the ocean has absorbed approximately 30% of the carbon dioxide produced by human activity. Without this absorption, atmospheric CO2 concentrations would be significantly higher than they currently are. In this sense, the ocean has been buffering the pace of climate change, absorbing carbon that would otherwise remain in the atmosphere. This buffering has a cost. When CO2 dissolves in seawater, it reacts with water molecules to form carbonic acid. This acid dissociates, releasing hydrogen ions and lowering the pH of the water. Since the pre-industrial era, average ocean pH has decreased by approximately 0.1 units, which corresponds to roughly a 26% increase in hydrogen ion concentration due to the logarithmic nature of the pH scale. This process is called ocean acidification. It is ongoing. It affects the ability of marine organisms to build calcium carbonate structures, shells, skeletons, and the frameworks of coral reefs. At lower pH, calcium carbonate becomes more soluble. Animals that depend on it must expend more energy to maintain their structures, and in sufficiently acidic conditions, structures can begin to dissolve even while the organism is alive. Pteropods, small free-swimming mollusks that are an important part of marine food webs in polar and cold water regions, have been documented with dissolving shells in ocean regions where acidification is most pronounced. They are often used as indicator species because their shells respond visibly to chemical changes. The biological consequences of continued acidification at projected rates are an active area of research. The full system-level effects are difficult to predict because ocean ecosystems involve complex interactions between thousands of species. Some organisms appear more tolerant of lower pH than others. Some may even benefit. But the organisms most sensitive to acidification, corals, bivalves, echinoderms, play foundational roles in marine ecosystems, and their decline would cascade through the food web in ways that are difficult to model precisely. The ocean also regulates climate through its heat capacity. Water has an exceptionally high specific heat. It takes a large amount of energy to raise the temperature of water compared to air or land. The ocean therefore acts as a massive thermal buffer, absorbing heat during warmer periods and releasing it slowly. This is why coastal climates tend to be more moderate than inland climates at the same latitude. The ocean moderates extremes. Since the 1970s, the ocean has absorbed more than 90% of the excess heat trapped by the enhanced greenhouse effect. The ocean has warmed. Its thermal structure has changed. The upper layers, which exchange heat and gases with the atmosphere, have warmed faster than deeper layers, increasing stratification and potentially reducing the mixing that brings nutrients to the surface. The ocean is not a passive backdrop to climate change. It is an active participant, absorbing both carbon and heat, and being chemically and physically altered in the process. Understanding how it will respond over the coming decades is one of the most important questions in Earth science. Rest with that for a moment. The ocean, working in the dark, absorbing what the atmosphere puts into it, steadily, without pause. The tides are caused by the gravitational pull of the moon and, to a lesser extent, the sun, on Earth's oceans. The moon's gravity creates a slight bulge of water on the side of the Earth facing the moon, and another, slightly smaller bulge on the opposite side, due to the relative weakness of gravitational pull at that greater distance combined with inertial effects. As the Earth rotates beneath these bulges, most coastal locations experience 2 high tides and 2 low tides per day, each cycle lasting approximately 12 hours and 25 minutes. The height difference between high and low tide varies enormously by location, depending on the shape of the coastline and the geometry of the ocean basin. In the open ocean, tides may shift water levels by less than a meter. In the Bay of Fundy in eastern Canada, a long, narrow bay that acts as a resonant funnel for tidal energy, the tidal range regularly exceeds 16 meters. The difference between high and low tide in that bay is greater than a 4-story building. Tidal forces also act on the solid Earth. The planet itself flexes slightly with each tidal cycle, a phenomenon called earth tides, with vertical deformation of up to half a meter. This is too subtle to feel, but it is measurable with precision instruments. The moon is gradually moving away from Earth. It recedes by approximately 3.8 centimeters per year, a consequence of tidal interactions with Earth's oceans that transfer angular momentum from Earth's rotation to the moon's orbit. Billions of years ago, the moon was much closer, and tides were dramatically higher and more frequent. The early Earth's coastlines, if any existed in anything like their modern form, would have been dominated by enormous tidal forces. The oceans themselves have a deep geological history. Current evidence suggests liquid water has existed on Earth's surface for at least 4 billion years, possibly longer. The earliest evidence for life in the ocean dates to approximately 3.5 billion years ago, in the form of fossilized microbial mats called stromatolites. Simple single-celled organisms dominated ocean life for roughly the first 3 billion years of Earth's biological history. The transition to complex, multicellular animal life, what geologists call the Cambrian explosion, occurred approximately 540 million years ago. In a relatively short period of geological time, most of the major animal body plans that exist today appeared in the fossil record. The oceans of the Cambrian period were teeming with strange, unfamiliar forms. Animals with 5 eyes, animals with spines projecting from every surface, animals with no clear equivalent among anything alive today. The ocean has been the site of all major evolutionary transitions in animal life on Earth. Life originated there. Complexity originated there. The first animals to leave the ocean and colonize land did so roughly 375 million years ago. Everything that walks, crawls, flies, or runs on land today is descended from organisms that once lived entirely in the ocean. The ocean is not just the current state of the world. It is the source of everything that lives in it. You carry some of that history in your body. The salt concentration in human blood plasma is similar to that of seawater. Your kidneys regulate it to maintain that similarity. The sea is in you, in a very literal biochemical sense. The floor of the ocean is not flat. Beneath the water lies a complete geological landscape: mountain ranges, volcanic plains, deep valleys, plateaus, and sediment-covered abyssal flats. In many ways, the underwater topography of Earth is more varied and more dramatic than anything on land. The mid-ocean ridges are the most extensive geological feature on Earth. They form a continuous underwater mountain range that winds around the globe for approximately 65,000 kilometers, longer than any mountain range on the surface. The Mid-Atlantic Ridge runs the full length of the Atlantic Ocean, from north to south, roughly tracing the center of the basin. The East Pacific Rise extends through the southeastern Pacific. They are connected, forming a single, continuous underwater ridge system. These ridges are where new ocean floor is constantly being created. At the ridge crests, tectonic plates are moving apart. As they separate, hot mantle material rises from below, partially melts, and erupts as lava. The lava cools rapidly in the cold seawater, forming new basaltic seafloor. This process, called seafloor spreading, adds new material to the ocean floor at rates ranging from about 2 centimeters per year in the Atlantic to more than 15 centimeters per year in the fastest spreading parts of the Pacific. The oldest ocean floor is roughly 200 million years old, much younger than the continental crust, which can be billions of years old. This is because oceanic crust is continuously recycled. As it spreads away from the ridges, it eventually reaches a subduction zone, where it is forced back down into the mantle and melted. The Atlantic Ocean did not exist 200 million years ago. It formed as the continents on either side moved apart, and it is still widening by several centimeters per year. The tallest mountain on Earth, measured from its base to its peak, is not Everest. It is Mauna Kea in Hawaii. Measured from its base on the ocean floor, Mauna Kea is approximately 10,210 meters tall. Only its upper 4,205 meters are above sea level. Mauna Kea is a shield volcano built up over millions of years by lava flows from a hotspot in the mantle beneath the Pacific Plate. Hawaii is not alone. The Pacific Ocean contains thousands of underwater volcanic mountains called seamounts. Most of them never reach the surface. They rise thousands of meters from the seafloor and then stop, submerged, forgotten. Some have flat tops, guyots, eroded flat by wave action when sea levels were lower, then submerged as sea levels rose and as the seafloor beneath them gradually sank under the weight of the accumulated rock. Seamounts create upwelling zones where nutrient-rich deep water is pushed toward the surface. They are biological hotspots, areas of elevated productivity in what might otherwise be relatively sparse open ocean. Deep-sea fish, sharks, and seabirds concentrate around them. Many species of deep-sea coral, some living for hundreds of years, attach to seamount surfaces and filter the upwelling water. Most seamounts have never been studied directly. Most have never been named. The seafloor is not a blank surface waiting to be explored. It is a complex, structured, biologically active landscape, most of which remains entirely unknown to science. The geography of the world beneath the water is, in a real sense, still being discovered. Humans have been navigating the ocean for a very long time. The settlement of the Pacific Islands, Polynesia, Micronesia, and Melanesia, represents one of the most remarkable feats of maritime navigation in human history. Starting from somewhere in Southeast Asia or Taiwan, ancestral Polynesian peoples spread across the Pacific in outrigger canoes, reaching islands scattered across an area of ocean larger than all of Earth's land masses combined. They reached Hawaii, roughly 4,000 kilometers from the nearest inhabited island, by at least 400 CE and possibly centuries earlier. They reached New Zealand, more than 3,000 kilometers from their nearest departure point, around 1280 CE. They reached Easter Island, one of the most isolated inhabited places on Earth, approximately the same era. Evidence suggests they may have made contact with South America. They did this without compasses, without GPS, without any of the navigational instruments that later European maritime explorers relied upon. They navigated by stars, by ocean swell patterns, by the behavior of birds, by the color and temperature of the water, by wave refraction patterns around islands that could be detected in the motion of the canoe hundreds of kilometers before land was visible. Some of this knowledge is preserved in living navigational traditions in Micronesia and has been documented by anthropologists and scientists working with traditional navigators. The mental models these navigators use are complex, multi-dimensional, and require years of instruction to develop. They represent a form of environmental knowledge that science is still working to fully understand. The scientific exploration of the deep ocean began seriously in the 19th century. The HMS Challenger expedition, which ran from 1872 to 1876, was the first major oceanographic survey. The ship traveled nearly 70,000 nautical miles, taking depth soundings, temperature measurements, and biological samples across all the world's major ocean basins. The expedition discovered thousands of new species and established many of the fundamental observations of physical oceanography. The data collected by the Challenger expedition filled 50 volumes when published. It took nearly 20 years to analyze and publish completely. It established that the deep ocean was not the featureless, lifeless abyss that most people assumed. It contained varied topography, distinct temperature structures, and, crucially, life at all depths sampled. Since then, the tools of oceanography have improved enormously. Satellite altimetry allows scientists to measure sea surface height to millimeter precision from orbit, which reveals information about ocean currents and subsurface topography. Autonomous underwater vehicles can now operate for months without human intervention, collecting continuous data over vast areas. Arrays of floating sensors called Argo floats, more than 4,000 of them currently active, drift through the ocean, periodically descending to 2,000 meters and back, measuring temperature, salinity, and pressure throughout the water column. Yet the fundamental situation hasn't changed. The ocean is large. The tools are limited. Most of it has never been directly observed. There is something quietly exciting about that. The deep ocean is one of the last genuinely unknown places on Earth. Every new expedition finds things that weren't expected. Every new depth record reveals organisms that weren't known to exist. The ocean is not a mystery that has been solved and is just waiting to be documented. It is actively, continuously surprising. If you could somehow be placed in the open ocean, far from any coast, and simply float at the surface, one of the things you would notice is how much of the world disappears. No traffic, no human voices, no mechanical sound of any kind. Just the movement of water and whatever sound carries through it from beneath. The open ocean has a characteristic ambient noise level that oceanographers have studied for decades. In the quietest parts of the remote ocean, the dominant sounds are wind-driven waves at the surface, the distant calls of marine mammals, and a low, diffuse background noise produced by billions of snapping shrimp in shallower waters. A sound that oceanographers sometimes describe as a continuous crackling, like a distant fire. There is also a sound called the hum, a persistent, very low-frequency acoustic signal in the oceans that was detected by seismologists in the 1990s. It has frequencies below the threshold of human hearing, and it appears to be continuous. Its origin was debated for years. Current scientific consensus is that it is generated by ocean waves interacting with the seafloor, infragravity waves that develop in coastal zones and propagate across entire ocean basins, creating a nearly continuous seismic signal that is detectable with sensitive instruments worldwide. The Earth hums, and it is the ocean making it do so. Human activity has added considerable noise to the ocean environment over the past century. Shipping traffic, sonar systems, seismic surveys for oil and gas exploration all produce sound that propagates through seawater. Some marine mammals are highly sensitive to this noise. Certain frequencies used in military sonar overlap with the communication ranges of beaked whales, and there is documented evidence linking naval sonar exercises to whale strandings in several cases. The ocean soundscape is, in a sense, a record of the ocean's state. What's living in it? What processes are active? What external forces are acting on it? Passive acoustic monitoring, simply placing hydrophones and listening, is an increasingly important tool in marine science because it allows continuous, non-invasive observation of large ocean areas. Scientists have used passive acoustics to detect earthquakes, to track whale populations, to identify illegal fishing, and to monitor the health of coral reefs. A healthy reef has a characteristic sound, a complex, layered soundscape produced by the snapping of shrimp, the grunting of fish, and the grinding of sea urchin teeth on coral. A degraded reef is quieter. The difference is audible. Sound as a measure of ecological health. The ocean speaking in frequencies we are only beginning to learn to listen to. Your body is quiet now. Your breathing has probably slowed. The sounds in the room, if there are any, have probably faded toward the background. This is what the nervous system does when it feels safe. It gradually attenuates incoming signals, filtering out what isn't necessary, letting the body drop into a lower gear. The ocean is doing something similar in a way, maintaining its deep currents, its thermal structure, its chemical balance, all of it operating at a slow, baseline pace that continues regardless of what happens at the surface. The surface is just the surface. Most of what matters is deeper down, quiet, steady, and going about its work without any need for your attention. If you're still with me, that's fine. Some nights the mind wants to stay a little longer before it lets go. There are a few more things I want to tell you quietly before we reach the end. New species are discovered in the ocean every year, not always in the deep sea. Sometimes in coastal waters, sometimes in areas that have been sampled before, but not thoroughly. In a typical year, marine biologists describe somewhere between 1,500 and 2,000 previously unknown species from the ocean. The current estimate for the total number of species in the ocean is somewhere between 700,000 and 1 million, with many scientists considering that a conservative lower bound. We have formal scientific descriptions for perhaps 230,000 marine species, which means, by even optimistic estimates, we have named less than a third of what lives in the ocean. The majority of life in the ocean is unknown to science. Some recently discovered species have been extraordinary. In 2023, a new species of beaked whale was formally described based on physical specimens. An entire species of large, air-breathing mammal that had been entirely unknown to science until an unusual specimen washed ashore and was examined closely. Large animals in the ocean still being discovered. The ocean also contains geological and chemical phenomena that remain poorly understood. Methane hydrates, ice-like structures in which methane molecules are trapped in a lattice of water molecules, exist in enormous quantities in cold, high-pressure sediments on continental shelves and slopes worldwide. The total amount of carbon stored in methane hydrates is estimated to exceed all other fossil fuel reserves combined. Under certain temperature and pressure conditions, these structures become unstable and release methane. Understanding how climate change might affect methane hydrate stability is an active and important area of research. There are also zones of the ocean called oxygen minimum zones, mid-depth regions where biological respiration consumes oxygen faster than circulation replenishes it, creating water that is nearly devoid of dissolved oxygen. These zones are expanding as the ocean warms because warmer water holds less dissolved gas and because changes in circulation reduce ventilation of these layers. Expanding oxygen minimum zones affect the distribution of marine life. Fish cannot enter them, and the animals that live there are highly specialized. The expansion of these zones is restructuring deep-sea ecosystems in ways scientists are still tracking. The ocean, in other words, is not a static backdrop. It is an active, changing system, geochemically complex, biologically diverse beyond full description, and deeply connected to every aspect of Earth's climate and life support systems. Science has given us an enormous amount of knowledge about it, and simultaneously revealed how much remains to be learned. That's a comfortable thing to sit with, I think. The fact that discovery is still possible, that the world is larger than what we currently know, that there are still first observations to be made, still first encounters with organisms that have never been described, still geological phenomena to be documented. The ocean will outlast us. It will continue absorbing, circulating, sustaining, and surprising long after any individual human is gone. That continuity is not something to be afraid of. It is something to find steadying. The deep water is moving slowly through the dark. The tides are doing what they have always done. The vents are warm at the bottom of the cold sea. The coral is building, one polyp at a time. And you are here, at the surface, resting. That's exactly where you should be tonight. So, we've covered a lot of ground tonight, or rather, a lot of water. We started at the surface, where phytoplankton produce half the oxygen in the atmosphere. We descended through the twilight zone, where billions of animals migrate up and down every day. We went deeper, to the midnight zone, where light is biological and darkness is total. We visited the hydrothermal vents at the ocean floor, where life exists entirely without the sun. We talked about the thermohaline circulation, moving water around the planet on 1,000-year timescales, about whale songs traveling thousands of kilometers through the SOFAR channel, about bioluminescence and coral symbiosis and the geology of the mid-ocean ridges, about the salt in your blood that echoes the composition of seawater, The ocean is not separate from you. Its oxygen is in your lungs. Its evolutionary history is in your cells. Its salt is in your blood. You came from it in the long run. Everything did. It is doing what it has always done right now. Cycling carbon, regulating temperature, sheltering an almost incomprehensible diversity of life in its depths. None of that requires anything from you tonight. Let your body be heavy. Let your thoughts lose their edges. There is nothing to hold together right now. The abyssal plains are quiet in the dark, kilometers below the surface, covered in a slow rain of organic particles drifting down from above. The Greenland shark is moving through cold water, unhurried, as it has for hundreds of years. The bioluminescent plankton are glowing somewhere in the dark water of a bay, responding to the movement of something that passed through them and is already gone. The ocean is vast and deep and mostly unknown, and it has been here for 4 billion years. And tonight, it is simply continuing, as it always has, as it always will, while you rest. Good night. Sleep well. And if you're still awake, that's okay too. There's more where this came from. Head over to the channel and pick something else. The stars are waiting, and so is everything else we haven't explored yet. Something in there will carry you off eventually.